Okay, I have 56 slides in 30 minutes, so I'm not going to keep the average. Okay, I'm going to take you back really about 16 to 20 years. There was just too much foundational stuff between 85 and 90 to talk about. And basically, this is what I've lived in the last 15 to 20 years, so I'm going to give you my humble opinion of what failed and what succeeded, and tell you where I believe the ideas really came from. There was a lot of original ideas, and as Scott said this morning, there were a lot of things that were imitated. So we'll first start with the communication model, layer 2 or layer 3, which is the best way to go. Datagrams or connections, who won, which is the best way to go. Different forms or modes of communication like point-to-point, multi-point, anycast, broadcast. And then what network layers have we seen in the last 15 years? And there's the plethora of network layer protocols, so to speak. And then we'll go into the routing protocols specifically, and I'm just going to focus on the unicast protocols because there was a ton of protocols over the past 20 years as well. If I have time, which I think I won't, I could talk about management and security, but I'm certainly not an expert at that, so there's much more qualified people in the room to talk about that, so we might have to skip the last part. Layer 2 or layer 3, what's the communication model? In the mid-'80s, bridging was really the popular form of doing communication or building networks. Transparent bridging was the Ethernet-based side of connecting LANs together, Ethernet LANs in particular, and source route bridging was used by IBM to connect token rings together. And they were fundamentally different technologies, even though they both ran at layer 2. At that time, the layer 3 network layer protocols were IP, XNS from Xerox, and AppleTalk. DECnet Phase 4 had been around for a long time in a lot of research and science environments, and DEC was at that time converting to DECnet Phase 5. Novell had IPX, and those were the deployments in PC-based networks. LandBridge 100 was actually the first multi-port bridge that came out. Before that, there were bridges, but they were only 2-port bridges, and they were mostly transparent bridging type bridges, which means if I see a frame on this interface, I examine the source address, and I learn that source address, so if anything's destined to that address, I know to send it here. Well, if you're going to send something from this source and you don't know that the destination lives on there from that frame, then you send it over to the other one. It was really easy. It was just 2 ports, go back and forth, and it was quite simple. But the LandBridge 100 gave you the multi-port bridge where there was 3 or more ports, which means you could build much more interesting topologies, layer 2 topologies. Of course, that was running at 10 megabits per second because that was the original speed for Ethernet, Phase 1 of Ethernet. However, IBM came out with Token Ring, and it was running at 16 megabits, so people were interested to get the extra bandwidth increase. But that required source route bridging, where the actual source host stack would actually find all the paths from a source to a destination, or from itself to a destination, and then be able to choose paths. So what happened at that point moving forward is DEC started doing 100 megabit per second LANs because FDDI just started coming out. Now we were having these bridges that were actually now being multimedia bridges. We could bridge between FDDI and Ethernet. Problem there was the encapsulation formats weren't the same, so you really had to do some really funny things. And there was all kinds of, and not only were the encapsulation not the same, they had different lengths, so you had to worry about MTU issues going from one media to the other. Then Vitalink took bridging one step further, and they wanted to bridge LANs across a point-to-point infrastructure, wide area infrastructure, using 56 kilobit links and using some arbitrary topologies. Well, as a lot of people in this room know, that loops in a topology in a layer 2 network are extremely dangerous. And layer 2 frames don't have TTLs, which means if packets go in loops, they continue to go in loops until you take something down. This is not good. Moving into the wide area, Cascade and 4 built frame relay and ATM switches. Switches here, you got to use that term very loosely because that's the trendy term now for bridges. In this talk, I'm saying a bridge is a layer 2 device that looks at MAC headers. Layer 2 switches or layer 3 switches confuse this matter quite a bit as well. But we're looking at Cascade and ATM, or Cascade and 4 is doing layer 2 things below the protocols that I mentioned. These bridges were kind of nice because they could support anything that a host would send out. It's just a frame, it's on Ethernet, it's on Token Ring or FDDI, you just send it. These bridges tried to be multimedia, but it was very difficult. On the other hand, LAT and NetBIOS, which really didn't have a network layer and no addressability per se at the network layer, were easier to bridge. But basically, there was just too much functionality put into bridges, and they were not scaling. They were melting down networks left and right. By the way, this talk is I put in a collection of badges or buttons that I've accumulated over the last 20 years, so I'm going to share all the buttons with you. And this is one that I had to keep because if you want to know if there's any router bigots out there, you're definitely looking at one right now. Routers did exist for a long time. The commercial success of bridges was continuing in the mid-'80s, but routers were doing things at that time. BBN built the original packet switches for military and national lab type applications. DEC was building DECnet routers, and Apple was building routers to do plug and play in work groups. And Novell and 3Com were building protocols, operating systems, and networks to do PC LANs, as I mentioned. At that time, the two premier router companies were Proteon and Cisco. They started building multi-protocol routers because they saw that bridges weren't able to live up to the task of doing all these different things. So they picked the largest set of popular protocols and they switched all those protocols at the network layer. But then again, due to the commercial success and the ease of use of bridges, Proteon and Cisco, as router companies from their heritage, felt that they needed to do bridging as well. And then you started seeing these devices which were called hybrid routers or brouters, which actually did bridging and routing depending, you could bridge for LAT and you could route for IP, and if you wanted to be able to do concurrent bridging and routing, you could actually do it for the same protocol. So these devices were getting pretty complex. Routers were better than bridges in these sort of attributes. Routers dealt with unlike media much easier. Don't forget, in the mid-'80s to late '80s time frame, we not only had Ethernet and Token Ring and FDDI, but we also had SMDS, X25, frame relay. ATM didn't hit the scene yet, but you could see where things are going. These were different medias from the network layer's point of view. And of course, routers could deal with arbitrary topologies. You could have lots of loops, lots of cycles in the graph, and they could deal with them much better because they did routing and addressing at a much more sophisticated level. Routers dealt with interorganizational connectivity much better. From a bridge's point of view, a port on my box is a port on my box. I don't treat it or distinguish it differently than any other port, where routers can. You can use demarcation points and say this is a boundary to another organization. I want to do route filtering, or I want to run an inter-AS routing protocol. Bridges were better than routers in these respects. They could build cheaper, price per port was an order of magnitude cheaper. I don't know why it was that way, it just turned out to be that way. Router vendors could have built routers really cheap, but it just didn't turn out that way. People like bridges because they had little configuration. Since everything was done at the MAC layer, you didn't have to configure subnets or aggregation or anything like that. The MAC addresses were always factory installed in all the devices, and you would just learn them during the data plane and do the right forwarding. And a lot of people thought you had to be an expert. And I guess the definition of an expert is if you have to do anything more than plug the power in, you have to be an expert. So a lot more bridge vendors than router vendors, and that caused the price per port to be driven down even more so. So we have three interesting battles that happened during this time frame. Which data link was going to win? Is it going to be Ethernet or Token Ring? And in the wide area, is it going to be ATM or POS? You heard John Curran say this morning that the best way to connect a router to a network is to connect it directly to the fiber. Nothing between the router and the fiber is the most cost-efficient way of doing things. So we'll see who won there. And then what device type to use? Should you use routers or should you use bridges? So the battle of Ethernet versus Token Ring existed for nearly 10 years. And it was basically IBM against DEC. It was really cool. And there was also these, this public domain set of people that was running TCP/IP that tend to like Ethernet as well. Workstation vendors, the Sun and the SGIs of the world adopted Ethernet mostly. And of course the PC vendors, the Novels and the XNSs also adopted Ethernet. So who won? It's pretty obvious that Ethernet won. And Ethernet now, they're building standards to go at 10 gigabits per second on Ethernet. So that's pretty amazing. The battle for ATM versus POS existed for about 5 years. When I worked at Cisco, a lot of people told me that if Cisco would have came out with POS 5 years earlier than they did, 4 systems wouldn't exist. I don't know if that's true or not, but that's what people have told me. The promise of ATM to the desktop was way too ambitious. There was just building a layer 2 infrastructure across the world and assuming everybody would have the same interfaces on all computers and all devices was just kind of unrealistic. But ATM did make it into the core. It was a nice way of connecting routers together because there was a point where DS3 was just not enough. People needed more bandwidth, and OC3 and OC12 was only available via an ATM interface via a 4 switch. So that's why people jumped to ATM-based cores. POS, or packet over SONET, is basically just running IP over the SONET framing layer, and it allowed high-speed connections between routers. This was beautiful. This really simplified things. It was just a data link with simple HDLC or PPP encapsulation, and you could run all your favorite protocols, your network layer protocols over it. So who won the battle? POS really won again for simplicity. It's amazing how far the KISS principle can take you. And nowadays there's more chip vendors doing POS and ATM because they see the curve going in the opposite direction. And it isn't amazing today we can use that old protocol called IP that's been around since the mid-70s that can run over a new layer 1 POS layer at 10 gigabits per second in the wide area network. That's quite amazing. So what type of devices should we use, routers or bridges? Well, the old adage is bridge where you can, route where you must. Bridges are good for work groups, and if you don't have too many bridge hops, you won't get into trouble. Because once you have a lot of redundancy, then you have to deal with spanning tree. And if you want to build an abstraction layer on top of that and run VLANs, you have to run a spanning tree per VLAN. Bridges are very good as a core fabric. A lot of the IXCs are basically just switches that connect routers into it. You can't get into trouble there, even though some of the IXC operators will say that alone is a challenge. Don't forget your broadcast and multicast applications. Basically, those sort of applications will unscale, or they won't be able to scale if you put them in a bridge network because packets are really going everywhere, regardless of all the fancy protocols you put in to try to help that problem. So I'd really have to change that first quote to say, use bridges and make them localize your subnets and route everywhere else. Just use them as a concentration points of hosts. And let's face it, switches really got popular because hosts wanted more than 10 megabits per second. And when you put multiple hosts on a LAN, on a shared media, collisions would give you effectively 30% of that. So by you having a point-to-point connection with your nearby switch gives you a full 10 megabits per second. And I think that's a useful function of a bridge. So who won? Well, I think routers will never lose. They've been around for 25 years, if not longer. Bridges are commercial success due to the Ethernet ubiquity. The simplicity of Ethernet caused switches to be used. And they're cheap and they're plug and play, and that still will, that goes along with the KISS principle as well. So the communication model, this is always fun. This went on for so many years. Datagrams versus connections. Is it better to have a connection-oriented network or a packet network or a connectionless network with less state? There was always these terms about hard state versus soft state, where TCP has hard state but IP has soft state. Well, in my point of view, me as a software developer, I have to do a malloc in both cases, so it's pretty hard to me. So some of the connection-oriented protocols were like X25, SNA, ATM, frame relay. These were all using connection-oriented protocols or, quote, hard state below the network layer. And then the various network layer protocols like IPXNS, IPX, AppleTalk, DECnet, all used connections at the transport layer were meant to be end-to-end and not between devices in a network. And the packets that were sent between the network were actually datagrams or connectionless entities. And then each packet would have its own addressability, and you could be able to reroute fast and everything. Datagrams is, you know, motherhood and apple pie. OSI wanted to support both types of models because there was forces from different parts of the world where CLNS was the connectionless network service and CONS was the connection-oriented network service. The OSI even wanted cons to work over Ethernet, and Ethernet is naturally frame or datagram based. And that adopted IEEE to build 802.2 as a standard. Connections, well, SNA was a proprietary protocol, so one company can control the technology, and they felt that connections would provide a predictable quality of service, and that's what they needed for the financial apps that were running over their protocols. X25 had a lot of influence from CCITT, where it was, again, more phone company orientation, where connections were important. In fact, in X25, a lot of people would think that X25 was a connection-oriented protocol itself. Well, it was actually a packet layer that actually built end-user connections, as well as building connections between devices on a network, like routers. And it was really the data link that was underneath it that was providing the reliability and retransmission and error control sort of functions. And there's some examples of X25 networks that were fairly large networks that were using internally packet switches that you didn't see. You couldn't see it. You couldn't do the trace route like Scott said and be able to see the hops inside of Telenet. But Telenet and TimeNet were US-based X25 networks. Transpac was a large X25 network in France, and DataPack in Germany. ATM and frame relay, like mines, were also from the circuit switch-oriented world. And signals and data and everything had to go over one technology over the entire Earth. And that just didn't make sense. Why, if I wanted to talk to somebody on the other side of the globe, why would there have to be 15 concatenated connections across all the devices between me and that person on the other side of the world? But connections could run over a datagram network, but it was harder to run datagrams over a connection-oriented network. And I've implemented this so many times, but trying to get IP to work over data links like X25, like ISDN, like ATM, where you're getting a fire hose worth of data, and you have to open up a VC to be able to get the packet to the next hop. Well, what do you do with all those packets that are coming in? Do you drop all of them? Do you queue the first one? Do you queue the last one? Do you queue the most recent one? What do you do? These are hard problems to solve in routers. So it was pretty unnatural to have datagrams run over a connection-oriented network. It was hard to have connections over each media type known to man. Some networks basically are not connection-oriented. And it's also hard to do QoS on each media type. Ethernet doesn't have a quality of service, so if you're going to run a connection-oriented service that provides quality service over something it doesn't, what good is it going to give you? And why do you need reliable connections on a reliable link? It's just putting too much belt and suspenders, and you're going to have inefficiencies and slowness. The performance of the system will just go down. Most data connection protocols run in data link mode. So for instance, if you want to run 802.2 over Ethernet, even though there is a cons mode to it, everybody uses unnumbered information frames, which basically is saying, oh yes, we can run TCP or UDP over this particular data link, but we'll just run UDP. So HDLC and PPP right now run over point-to-point links in a connectionless mode. Most of the dynamic connection mode protocols run in PVC mode. So the fire hose problem that I just mentioned usually doesn't happen because the PVCs are set up ahead of time. Your next hops are known through your routing protocol, and so when you're ready to forward data, the PVC or the infrastructure is there and ready at your service. Datagrams. Well, most of the host-based vendor protocols are datagram oriented, and all those protocols you see up there are ones that actually send datagrams into the network at the network layer. And the ubiquity of Ethernet and other datagram-oriented data links allow datagram network layers to run effortlessly over links. And of course, this is the datagrams and packet switches require less state. Well, a routing table versus a socket or a connection identifier is pretty much the same, so maybe it's a moot argument or a subtle argument. So who won, datagrams versus connections? In my mind, it was datagrams. Let's go into communication modes. There's two-party communication, which is the most popular form of communication, point-to-point. There's one-to-many, many-to-many, few-to-many. That's all the multi-point mode. And then there's this closest party communication. Let me get to the closest server, also known as Anycast, which we've exploited really only in the last, I'd say, 5 to 7 years in IP and trying to formalize it in IPv6. And of course, all-party communication is broadcast. How many people in this room have tried to send a packet to everybody on the internet? And why would you want to do that, and why is that useful? So within a reasonable scope, is broadcast useful? So layer 2 datagram protocols could do unicast, multicast, anycast, and broadcast. The LAN itself worked really well. And it was a really passive type multi-party communication model, because you would just program your LAN controller, and then the LAN controller would just listen on the wire for those addresses. You didn't have to go tell somebody you wanted to listen to something outside the box. Layer 2 connection protocols could only do unicast and multicast. Like ATM had some form of doing multi-point VCs, but it was a switch VC, and you'd have to set it up ahead of time. But really, when you were running in PVC mode, you had to simulate this multi-point sort of communication by doing replication over the same physical link, and that was not good for bandwidth savings. So it was really only the network players that could really support all these really different modes in a robust and scalable way. Everybody will claim that they support it, but in a robust and scalable way, mostly the network layer protocols could do it. And not all network layer protocols could do it. And if you look at that list right there, XNS had point-to-point communication, but only really had link-local broadcast. And DEC had point-to-point, link-local multicast, and link-local broadcast. And AppleTalk was really the only one that really went to a multi-hop multicast. Early on, they had broadcast and multicast applications because of the type of applications and the ease of use they wanted to provide to the user. But when you look at everything put together, really IP and IPv6 have all the communication modes, and they've been studied and experimented and are really the more robust and scalable way of going. So for mode support, who won? Well, like I said, AppleTalk really had the applications to back the multicast mode. The chooser, the directory services, print sharing, file sharing, all that stuff. You have to give Apple credit that they were able to deploy that stuff much earlier than IP did. But IP learned from that and used those sort of things. A lot of the ideas of DHCP came from AppleTalk on how to do address assignment. You know, DHCP does not date back to the mid-70s. It's one of the later protocols that came into the Internet suite. IP has the scalability and has the more robust network layer support because the whole world works on IP, not just one vendor. And you get the good and the bad associated with that. So I think all other variants failed. And I think IPv6 is trying to have the same promise as IPv4 gave, and that will remain to be seen with more experimentation and deployment experience. So why so many network layer protocols? Well, at the time, there was really no rapidly defined standards. IBM was around for a long time, and they had to focus on their applications, and they wanted to control their own destiny, so hence SNA was proprietary. Xerox was out pretty much at the same time and felt the same way, and they had a lot of experience building SBP as the transport. And Novell was going after a market that they saw growing. PCs were getting cheap. Ethernets were simple to plug in. They were going after that market. They couldn't wait for the ITF community or the TCP/IP community to come up with standards, so they went their own way. And of course, everybody knows that DEC was been around for a long time, and they had their idea. In fact, DEC had a lot of good influence into the IETF over many years, over many generations of people and protocols. And of course, Apple was doing the same thing that Novell was doing, but they were doing it with their proprietary gear, and they were building really cool stuff. So that's why everybody was going off their own way. And at the same time, there was this TCP/IP protocol suite that was in the military and research labs, and a lot of the Unixes implemented them. A lot of the like 4.1, 4.2 timeframe of Unix BSD had XNS, and a lot of those implementations were a lot of people were transitioning from an XNS protocol stack to IP. And the new workstation vendors at the time was Sun and SGI. They had support for TCP/IP. So all the public domain code was all running over IP, and it was in this small community of researchers and scientists. And that's how TCP/IP started. And there were router vendors back then that were building routers for the good of the internet and not necessarily for their commercial success, even though they all became fairly successful in their own right. BBN, ACC, Bridge, Proteon, Cisco are some of the early pioneers. And you know, DARPA and NSF put a lot of funding into this stuff, and that's why IP became the de facto. A lot of people pride themselves on calling it the de facto standard because it just permeates all this real reality and what's going on. And you have to admit that the internet really didn't take off until it was embedded in Windows 90. TCP/IP was embedded in Windows 95. That, coupled with the web becoming popular, really made it take off to the huge masses of people, and hence we have the big commercial internet as we know it today. Well, what was wrong with TCP/IP? It wasn't an international standard. ISA was building full-blown standards, not just at the network layer, but all the way up the stack. Layer 1 all the way up to layer 7, or arguably all the way up to layer 8, which is the political layer. The U.S. government proposed GOSSIP, which was a mandate for new contracts. We cannot buy your products unless you have an OSI stack. It doesn't need to be turned on. It doesn't need to be configured, but as long as it's in the implementation, we know someday we can go to it. So DEC was a huge supporter of OSI, and DECnet Phase 5 was a complete implementation of OSI. But what about the internet applications that people grow to love? Could they run over OSI? Well, I mean, in theory they could run over it, but since there was all these other, virtual terminal and FTAM, which were the equivalents, we don't need those applications because we're just going to duplicate it on the OSI side. So bottom line, it just took so long for vendors to field OSI products, and there were a lot of people in the IETF that actually tried to build CLNS-based networks and did to a certain extreme. We had a dual stack internet for a long time in the late 80s, early 90s. It was dual stacked and it was CLNS and IP. But I always remember that the only CLNS packets that were floating around were ping packets to test the reachability. So OSI just didn't happen, and it was really the standard by the build your protocols by committee sort of way of doing things. And IETF's model was always rough consensus and working code. And a lot of people say, well, there's pros and cons on going both ways. But when the IETF or the internet community built a protocol, you knew that it was tested out already, and it just wasn't something on a piece of paper. So that had a lot of merit, and that's, I think, part of the success of the internet. So who won? Which network layer protocol won? It should be obvious: the power of TCP/IP. So in the mid-90s, IP had some problems, or at least there were some perceived problems. 32-bit addresses, that's not enough address space. It's too hard to reassign addresses to routing domains. How are you going to be able to switch from one ISP to another? Are we going to get vendor lock? The routing domain multi-homing problem was exploding the routing table size. The sky is falling. We better do something right away. When was this, Sue? In 95? 94, 95, 96 time frame? Well, we're still here, and I think the network is as good as it's ever gotten. I mean, what other network could move around as much spam as we have? How do we solve the IPv4 problem? Well, there was an interesting committee. I think Paul will talk a little bit about this, but there was this committee called ROAD, Routing and Addressing. There were a bunch of people that got together to figure out how to do some things. LNAT was a NAT-like way of solving the problem, and IPay was a way of putting encapsulation into an IP and using another level of 32-bit addressing, the same 32-bit addressing that we do use today, but it was on top of what was going to be in the user's 32-bit headers. So that was one way. OSI was also considered as a replacement to IPv4 again. And then those were the various proposals underneath: SIP, PIP, CATNAP, TUBA, Nimrod, and Big Ten. Big Ten was probably the protocol that had the most, could have had the most success in the shortest amount of development time. Basically, a bunch of people got together at an airport close to O'Hare, got it together at a hotel close to O'Hare Airport just to come up with a scheme. And at that point, it was an argument between variable length addresses and fixed length addresses. So what happened is SIP was a proposal for 8-byte addresses. And so based on the influence from Big Ten, it was obvious that 8 was too small and variable length wasn't going to happen. So the compromise by committee was, let's have 16-byte addresses. And that's how IP version 6 was born. And there was more merchandise that became available. Actually, what TUBA stands for is TCP and UDP with bigger addresses. This was a way you could run all the internet applications and TCP and UDP over a new network layer and its associated protocols. And that was going to be CLNS, IS to IS, ES to IS, and all those protocols. And funny, IS to IS is a very popular protocol today. What's good about IPv6? Well, there's no ad hoc standards anymore. A lot of people said ARP was specified because the They looked at the C code and then translated it into English. Those sort of things aren't happening in IPv6. It's really more of a standard-based, it's kind of merging OSI and IETF and using the best of both worlds or the worst of both worlds. So it was designed both by host and router vendors, and like the IETF way, it was built through implementation. Okay, we're not going to say what's bad about IPv6. So I'm like severely behind, and everybody wants to hear about IGPs. Okay, so let's go to routing protocols real quick now. What about the plethora of routing protocols? Did we have too many? Did we learn from our past sins? Well, we started with, okay, this is going to be the nutshell of everything. We started with RIP and EGP. That defined the IGP-EGP split. We needed two protocols, one that runs in the domain, one that runs between domains. Everybody liked RIP because it was easy to understand. You could do route filtering. GGP and EGP were the inter-AS protocols that were run in the early days of the MILNet and the ARPANET. Okay? BGP was the successor of these protocols. Okay, this was the RIP-EGP couple. They ran for a long time in a lot of vendors' products. Cisco thought that wasn't sufficient. They had to provide a proprietary solution to it. KT was the public domain version of it. Proteon came out with OSPF, and IETF was working on BGP. Sue's going to talk about BGP. There was a war between IS-IS and OSPF. Bottom line is, enterprise runs OSPF, service providers run IS to IS. And I could talk to you in the bar tonight why that was useful. And this was the first set of vendors that implemented OSPF. Sue's going to talk about BGP. Even though OSPF and IS were becoming deployed, the router vendors believed that there was still a need for their own protocols. And so Cisco was working on EIGRP, Novell was working on NLSP. But finally, what happened in the late 90s is more IGRP networks moved to OSPF, and today we can say we really have three protocols that are running, and they're very mature implementations from dozens of vendors, and that's OSPF, IS, and BGP. Definitely no mention.
You did it.
Okay, can I do my last slide?
Yay!
My last slide?
You got it? He gets his t-shirt.
So as a software developer, I believe that the internet is succeeding because of open source, public domain, learning through experience and evolution, and you just can't live without it anymore. Thanks, Vince Cerf.